EnterCalc 3D has the ability to perform reinforced concrete plate design using wood armor moments. And to take a look at how this works, we'll use this model, a simple single bay, single story reinforced concrete frame with some intermediate beams and a mesh of plates integral with those beams. So we pick up some multi-span slab action. We won't talk a lot about the details of model building here. That's not really our focus in this video, but we do need to have a model that analyzes and produces results. So that means we have to have a stable model. All members have to have section properties, materials, we have to have loads applied, and the analysis has to complete properly. The one thing that we do want to focus on for a second is load combinations. So here on the Create tab, I'll come to Load Combinations and just point out that the default load combination comes along for the ride for free. It always runs and there's nothing we need to worry about there. What we do want to focus on is the fact that I've generated many ACI load combinations right here in the program. And all of those ACI load combinations are set to run. They're all set to yes for a P delta analysis, and they're all set to yes for concrete design. So they'll all be used when we go over to the concrete design tab. So we don't need to make any changes there. The next thing that we'll do is we'll get some analysis results. So on the analysis tab, I'll use static analysis, and this takes about 45 seconds to run. So I'll click the button and then trim out the wait time to shorten up the video. Okay, so now we have a completed analysis, and I'll click Close. Then we'll just clean up the view so that we can see the analytical model. And we'll come to Concrete Design, and we'll just work our way through the buttons. Starting with RC Materials. This lists the materials that have already been defined in the model. All the members that we're looking at are of this Concrete 30 material. The thing that's important to note in this version of the materials table is that it doesn't have to do with stiffness properties. Instead, it has to do with strength properties. And so what this does is it allows us to specify F prime C, Fy for the primary reinforcing, and Fy for ties or stirrups if we happen to be looking at beams or columns. I'm going to leave these values set as they already are, so I don't need to do any work on this one. I'll just click Cancel. The next button is RC Model Design Criteria. This is where we select which code we want to use. We can skip column design parameters and beam design parameters. Since we're focused on plate design, we'll just look at this area right here. This is where we establish the minimum reinforcing ratio for the slab top steel and the bottom steel. The only thing that I'd like to mention on this area is that we're used to the number 0.0018, but the program is set up to interpret these fields as being percentages already, so we want to enter this as 0.18. I'll click Cancel. Then we'll come to Reinforced Concrete Design Criteria. We can skip over beam and column and just go straight to plate design criteria. In this table, we can create as many different plate criteria as we need to accurately describe all the different plates in the model. Because all of my plates are the same, I only need one criteria. We can give them meaningful names. I've just left this set to default. And the purpose of this table is to locate the rebar. So we can see that we have dimensions to locate what we call X and Y bars, and we'll talk about the meaning of those directions in a minute. And we have bottom X, bottom Y, top X, and top Y. The one thing that I like to point out in this table is that these values are interpreted as being the edge of the concrete to the centroid of the bar. So if we have clear cover in mind, we need to make sure that we add that 1/2 of a bar diameter to get to the centroid of the bar. Now I'm satisfied with all these values for our purposes, so I'll just click Cancel. The next button is Exclude Concrete Elements. This tool lets us specify to the program which beams and columns or shells we do or don't want designs for. I've already gone in and told the program that we don't want designs for the columns or for the beams, but we do want designs for the shells, so I don't need to do anything with this function. The next button is Cracking Factors. This is where we can specify the cracking factor that we want the program to use for members or for shells. It's handy because it has the little reminder table down here, and I've used that to previously specify a cracking factor for our plates of 0.25 based on the ACI recommendations. So again, I'll just click Cancel. The RC Design Properties button offers options for beams, columns, and for plates. And these are just simple ways to, in bulk, apply previously defined criteria, inclusion or exclusion status, and cracking factors. That's already been done for us, so I'll click Cancel. The next button is RC Member Input. We're not doing any beam or column designs, so we'll skip that one and go straight to RC Plate Input. This table lists all the shells in the model, and it shows us what design criteria has been applied to each shell, the cracking factor, and the inclusion or exclusion status. And if we want to make changes, we can click in any of these cells and make edits, but everything is currently set the way that I want it, so we'll click Cancel. That's all the input that we need at this point to perform the shell design, so we can click the Perform Concrete Design, and you can see that in no time at all it has zipped through and produced designs for all of our shells. So now we can start to take a look at some results. On the Concrete Design Output button, we have options to look at wood armor moments and to look at plate results. So if I go to wood armor moments first, we can see a table, and this lists for every shell in the model the bottom MX and MY and the top MX and MY values, as well as the controlling load combinations that produce those moments. And again, these are for the wood armor moments that are used to size the steel. If I come back to RC plate results, we can see a table similar that lists the thickness of each plate, the concrete strength and the rebar strength, and then the bottom MX and MY values and top MX and MY values, as well as the areas of steel to address those respective moments. So those are handy tabular forms for the output. We'll skip the flexural interaction button because we don't have any columns. Come over to Concrete Design Diagrams and go directly to RC Plate Envelope Contour. This tool lets us graphically view wood armor moments as well as required plate reinforcement. So let's take a look at wood armor moments, and specifically with respect to the bottom X direction, and then we'll turn on the surface diagram as well as a display of the values and click OK. So we can see that we have a gradient or a distribution of moments here that are being used for the design. And this is probably a great time for me to show a couple of handy tips. One, if I come back in to this contour and I want to clarify it, I can choose this None or Erase option, and that's how we turn off the diagram. The other thing that I'd like to mention is we've seen reference to this X and Y direction, and it would help if I turned on the shell local axes. And then let's just zoom in on one of the shells so we can see that there's a red direction, a green direction, and then the blue points upward. So what I do is I use the global axis triad down here in the corner to refresh my memory that red means X. So the red that we see on each shell represents the local X direction. Likewise, if I look at the global axis triad and I see green, it reminds me that that's the Y direction. So that means that the green axes are the local Y directions. So this helps us to understand the meaning of plate X and plate Y directions. And I can clarify that view just by toggling off the display of axes and then bringing the model back into view. So we were looking at the plate envelope contours that are available. And another thing that's interesting is to look at the required plate reinforcement. We'll still use the bottom X direction, and we'll take a look at surface and value and say OK. Now this doesn't show very much of interest to us because everything is controlled by the minimum steel. But if we choose to look at the Y direction for the bottom steel, we can now see that the steel that runs in the plate Y direction across the view here varies, and that's because we have a 3-span continuous slab, so the spans on the outside don't feel as much moment and therefore don't require as much steel. We can see that they're controlled by minimum steel, but this center bay is the one that tends to feel the moment and requires a little bit more steel, and so we can see that requirement shown in red. Likewise, if you come back to concrete design diagrams, you can view plate reinforcement required for, say, the top in either direction. And this will show us some colors out on the corners. That's a result of the continuity that's being experienced by the shells connected to the columns and so on. So you can explore all 4 of the directions and surfaces and figure out what steel is required in any of the shells using these diagrams. The last thing I'll mention is that Concrete Design Tools is available. It provides a database and a K calculator, but these don't have much to do with plate and shell reinforcement or plate and shell design. And the unity check function has no purpose in plate design either. So those we can just kind of ignore. So hopefully that's been a helpful look at what's available for plate design using EnterCalc 3D.